The Fourier transform is our next subject, and we are moving from Fourier series that represents periodic signals to Fourier transform that follows a similar representation of Fourier series to represent non-periodic signals. But what we normally do is to limit our non-periodic signal to finite duration, such that the function is considered to be going to zero when the limits are exceeded, that is beyond our period. The signal x of t goes or becomes zero when you have exceeded your limits of observation, or yeah. So that being said, we are saying that such a signal is shown in figure 5.1, which is just in the next page, is right here, but I have redrawn it here for our convenience. And we are saying that such a signal as this one, we said that let x of t be a periodic signal formed by repeating xt. So notice that I have a different version of x of t here. That is x underscore t naught of t is now considered as a periodic signal, or rather we are repeating this signal every t. This is our t naught. So if we repeat our signal every t naught seconds or times, then we are going to develop a signal that takes the form as though it is repeating itself. So we are saying that such a signal, let x of t naught or x of t naught be a periodic signal formed by repeating our xt with a fundamental period xt naught that is shown in figure 1b below. So if you repeat this signal, you're going to have another signal that takes that shape, another signal that takes that shape, and that signal is shown at this point. And I think I want to make a correction that the limit of our signal is t1, whereas our period of observation is t naught. So that is the correction I want to make, that we are not saying that t1, or rather this is supposed to be t1 over 2, this is t1 over 2, so the whole period is t1, or the whole time where x of t is not 0 is equals to t1. But then we are saying that you would ordinarily want to repeat your time limited signal every period, and you might set your period to be at that point, such that this would be t naught over 2, and of course this other period would be t naught over 2. And therefore we are saying that if you have t naught is bigger than t1, and you're saying that x of t goes to 0 when t is bigger than t1, then this condition would be met. And therefore we are saying that we can make our non-periodic signal to appear as though it is periodic every t naught. And therefore we are saying that if we let now our period of observation, our t naught, to approach infinity, then we can develop equation 522 that says that the limit at t naught approaches infinity of our function x or x subscript t naught of t will actually be treated as though it is the same as our original signal that was not periodic, which is x of t. And therefore, if we now try to perform the Fourier series representation of our x of t with subscript t naught, then we are going to follow a similar procedure that simply introduces a complex exponential coefficient ck, and just define our x of t in a similar manner. So the following steps we are going to be following is to see how can we develop a Fourier transform, we call Fourier transform, from Fourier series. And that is where we are getting the idea that we are moving from Fourier series to Fourier transform. So similar to the way we derived CK, and I guess we may not have derived CK, but we stated that CK for a Fourier series, that is our complex exponential coefficient, we said that it is always given by 1 over period t naught integrate and our x of t integrated over 1 period t naught, and then you introduce minus j k omega naught t dt. This is how we define our complex coefficient for Fourier series ck, and taking a similar approach, we can develop our ck as shown in figure 524. And of course, we might have already seen, I'm not sure if I have mentioned this one, that our limits can be considered to be starting from 0 to t naught, or we can also consider from minus t naught over 2 to t naught over 2. So these limits of integration are considered to be the same. And therefore, we are taking the limits of integration as such. And we have just replaced our x of t with x of x subscript t naught of t. And therefore, we are just trying to see how can we develop a Fourier representation of a non-periodic signal in a manner that we did for a periodic signal. So of course you can see that our x subscript t naught of t is equals to x of t, and our period is now limited by t naught over 2. And therefore, from this observation, we can also confirm that our x of t is equals to 0 outside our region. T is less than t naught over 2. My apologies for interruption. I was saying that our limit, of course, we say is x of t goes to 0 for our period t naught is less than 2, just like I explained that we are, I think I have rubbed. So we are saying that if we set our limit t naught over 2 to be at this point, we can see clearly that x of t goes to 0 beyond this limit and beyond this limit. So having said that, we are saying that equation 524a, this equation now, which is defined, which is the complex Fourier series coefficient now for a non-periodic signal x subscript t naught of t, we can actually transform it by saying that our x of t naught of t will be simply the same as x of t, as you have seen in this expression. And for that reason, our equation 524, we can displace this with x of t. And what that will give us is that equation 524a takes the form of x or 524b. And the only difference is that we have replaced x of t naught of t. And then there's something that we'll actually observe in this situation, that since we are saying that the limit of t naught so when we replace x of t naught with x of t, we change our limits of integration from t naught over 2 minus to t naught over 2. And now we end up with, we are replacing this with infinity, because we are saying that t naught is approaching infinity, and therefore t naught over 2 will approach infinity, and minus t naught over 2 will approach infinity. So for that reason, we are changing our complex Fourier series coefficient ck from having x of t from being integrated over the one period limit to being integrated over the entire period as defined in equation 524. And for that reason, therefore, if we define this term, we give it a new definition. We say that this is equals to x of omega, or this one. That tells us something, that we can represent our complex Fourier coefficient ck in terms of this term, which is now defined in equation 526. And now from equation 526, if we substitute this equation into our definition of Fourier representation of our non-periodic signal x of t naught, which is defined here, what we find now is that x of t naught may be, we are just replacing equation 526 with equation 523, where we said that x of t naught, we are now replacing ck that we had in our definition to be k is equals to minus infinity to infinity. We had ck here, and we had exponent of j k omega naught of t. That is our definition that we had given earlier for a non-periodic signal. And therefore, since we have obtained our value of ck, if we plug it in at equation 523, which is this one, we will definitely get equation that replaces ck with 1 over t naught x of k omega naught. And now having that expression, we can just do some manipulation of this 1 over t naught with an intention of removing this term to being just a plain omega. So that is what, so that when we attain the representation with x being represented with omega, then we are going to call this one x Fourier transform. So what we are going to do is that we want to remove a function of x of k omega naught to being represented with this form. And what we start with by doing is just try to manipulate this 1 over t naught, and we can say that 1 over t naught can be represented as 2 pi and then multiplied by 2 pi over 2 pi. And this by itself is equivalent to omega naught. And therefore, we end up with 1 over 2 pi outside our summation, and then we have our omega naught on this side. There is something that we are going to see very shortly, that as t naught approaches infinity, just as we have said in our integral earlier, at this point we say the integral is approaching infinity. So in this case, therefore, our t naught is also approaching infinity, and for that reason, this term also becomes 0, because anytime we have 2 pi divided by infinity, which is our t naught, it will tend towards 0. So we are saying that this term approaches 0, and therefore, if we let our omega naught to be infinitesimal, we are saying that when this approaches 0, then our omega naught becomes very, very small, that we can, instead of considering it as a full value, we can consider it as infinitesimal. And therefore, with that infinitesimal representation, it allows us to get from to leave from summation towards integration, and infinitesimal value becomes derivative. So having said that, we are saying that equation 5 to it now actually takes the form, as I have mentioned, that the limit as this change in omega, or infinitesimal omega, which is representing our angular frequency, as it approaches 0, this summation will become 0. Will become an integral. And our k of delta omega will be treated as though it is now omega, because what you are going to see here is that the sum on the right hand side, which is this one of this equation 529, can be viewed as an area under the function this one. So if we treat this summation, we are adding very small infinitesimal elements defined by k delta omega. Therefore, we can actually see that this small region that is shaded may be considered to be on our the scale that is towards the right. We can consider that it is divided in so many delta omegas, the one we are calling infinitesimal, and then they are increasing with k. So this k is equals to 1, k is equals to 2, 3, 4, all the way. And therefore, this small area is represented by x of omega, ejk omega naught, ejk omega delta omega. Because we're saying that the area or the width of 1 can be said to be equals to delta of omega, the small infinitesimal increase in width. So having said that in so many words, I want to say that our equation 529, and having explained all that, I can clean up my board and say now that our equation 52827 develops and agrees with this situation, that we are changing our x of t to our x of t naught of t to become our x of t as our limit of our period approaches infinity, and therefore our summation becomes integral, and our x of k delta omega becomes a function of omega. So that, in few words, having said that, we are saying that we can treat k delta omega as omega, and this term again becomes omega, and our infinitesimal change in omega becomes delta omega, and therefore our function takes this form. And now this is our most important function that we are trying to derive, that says that this is how you represent a non-periodic signal x of t using the Fourier representation. And this, what we have defined as x of omega, is actually called the Fourier transform of x of t. So having defined the Fourier transform, we come to a section that allows us to have a pair. One is for Fourier transform, the one we have defined here as x of omega, and we notice that that is capital X of omega is the Fourier transform of small x of t. And so we are simply saying that we have defined a function x of omega, which is we defined earlier that x of omega of is a Fourier transform, and normally indicated as f of x of t. This means Fourier transform of x of t, and is defined. We defined this equation in equation 524. This is that x of omega, capital, always remember that this is capital, is equals to minus infinity to infinity of x of t e minus j omega t dt. And we can also define another transform that now represents the one that we have defined in question 530, that says our non-periodic signal x of t is represented by the Fourier transform x of omega, but now at the integration. So we are saying that now that this is the inverse Fourier transform. We normally say that inverse Fourier transform of our x of omega. And of course, we have defined this one to be in equation 530, and it simply says that it is 1 over 2 pi integral from minus infinity to infinity of x of omega ej omega t. So this is equals to 1 over 2 pi from minus infinity to infinity of x of omega ej omega t dt. Of course not dt, but now is our function of omega. So the omega. So this is the definition of inverse of Fourier transform. Inverse Fourier transform, and it simply expresses our non-periodic signal x of t as an integral of Fourier transform x omega integrated from minus infinity to infinity with this term introduced, and Fourier transform as just as we have defined as from the integral from minus infinity to infinity of x of t, our non-periodic signal. We notice that now this one is negative ej omega t, whereas the inverse Fourier transform is positive ej omega t. And that forms our Fourier transform pair that we normally indicate that you can transform from time domain to frequency domain, or you can always Fourier transform between this, and this is called Fourier transformation. And you can always move from one form to the other. A similarly related concept is that of Fourier spectra. And the Fourier spectra allows us to relate our non-periodic signal x of t to have to determine its spectrum or representation in frequency domain, and that is the one that we refer to as the Fourier spectra. And we are saying that if our Fourier representation of x of t, x of omega, as shown in figure 534, we say that in the first place it is complex, and therefore it can be represented as having a magnitude x of omega modulus, and the phase that is represented by exponent of j phase phi of omega. And by analogy with the terminology we used for the complex Fourier coefficients of periodic signals x of t, we are saying that the Fourier transform x of omega is of a non-periodic signal x of t is the frequency domain representation of x of t, and is referred to as the spectrum or Fourier spectrum of x of t. And therefore, the quantity, the magnitude, the quantity x of omega magnitude is called the magnitude spectrum of x of t. And the phi omega is called the phase spectrum of x of t. So under you can see this represents the magnitude, and this represents the phase, as I have already indicated. So if x of t is a real signal, we are saying that we are going to be representing this real signal with a complex signal x of omega that has a phase that has a magnitude x of omega, and the phase component, which is represented by phi of omega. So having said that, then we can characterize each of these terms, and we say that it follows from the definition, this one, that if you are x of omega, or the Fourier transform x of omega, the omega was evaluated from the negative side. Therefore, what we would change here is the negative sign that was there to become positive. And what we actually observe is that the negative value would be represented by a complex conjugate, because we know that if a negative value is represented in the exponential form, we say that it becomes the complex conjugate, the one that we are representing with a star. And therefore, from our knowledge of conjugation, we can say that the magnitude remains the same. And from that observation, we simply say that the amplitude spectrum represented by this term is an even function. On the other hand, the phase is going to be an odd function, simply because it's the negative sign takes the form as indicated in figure 536b. And just as we saw in the case of periodic signals, we have sufficient conditions for the convergence of Fourier transform x of omega. And they are the following, and which are referred to as the Dirichlet conditions, just as we refer to them during the Fourier series representation. And we're saying that the first one is that the Fourier transform, or the x of t, must be absolutely integrable, such that it would satisfy the condition that its integration over time would always give you a non-infinite value. And number two, the x of t has a finite number of maximas and minima within any finite interval. And lastly, that if x of t has finite number of discontinuities within the interval, and each of these discontinuities is finite. There's a point that we should, of course, observe, that these conditions guarantee the existence for a signal, or of the Fourier transform for a signal. But if we introduce impulse functions in the transforms, then we are going to find we have signals that do not satisfy these above conditions. So, but that is only exception that we have. At this stage, it is considered that you are familiar with the concept of Fourier transform. And therefore, you might try to see a connection between the Fourier transform and the Laplace transform. And it is very straightforward that the Fourier transform is defined as in question 538, and the Laplace transform is defined in question 539. And the obvious difference that you see is that one we have j omega, and in the other case we have s. And therefore, we are saying that we consider S Fourier transform to be a special case of the Laplace transform, where S is equals to j omega. So in general case, we normally say that S might be sigma plus j omega. So in the event that sigma is equal to 0, then we say that Fourier transform becomes the Laplace transform. Or rather, the Laplace transform that is represented becomes the representation of S, meaning that our sigma is taken to be 0. And that is a very good comparison, because if you have a Laplace transform, you can always get its Fourier transform representation as we can see in figure 540.